Hello everyone. Let's take a look at an example for the applications of vectors. And specifically in this case we're going to be using the resultant vector to help us find our answer. So I have an example here. We have an airplane. It's flying at an airspeed of 310 knots on a heading of 50 degrees. So those two pieces of information together, we have a speed, we have a direction. Combining that, we can represent that with a vector. We also have a 78 knot wind from a true heading of 125 degrees. Again, a speed and a direction, putting those together, that is another vector. Determine the speed and direction of the plane relative to the ground. So finding the actual speed, the actual direction that the plane is heading, that's going to be represented by the resultant vector of these two things, right? We have two different forces here. We have the plane flying at a certain speed in a certain direction. We have the wind acting on the plane. So the resultant vector is what we're looking for. Okay, so to start off, what I want to do is I want to represent both of these things as a vector. So I'm going to draw two separate diagrams just to differentiate between the two, and then we'll put them together to find the resultant vector. So the first thing, let's start with the plane. So I'm going to draw a little set of axes here. Just a little sketch, doesn't necessarily matter what it looks like. So we'll represent that as north, and then it's telling us that it's flying at 310 knots. So that's the magnitude of the vector, that's the length of it. And then at a heading of 50 degrees. So when the direction is written like this represents a true bearing, a true heading. So what that means is we start pointing north, and then we rotate this much clockwise. So starting from the north, we'll rotate 50 degrees towards the east. And then let's just we'll kind of color code this here. So starting from the north, 50 degrees towards the east. So then this angle, this is the 50 degrees. And then the length of this is 310 knots. Okay, so there's a vector, represents the plane. Let's do the same thing for the wind. Now I just have to be a little bit careful with the wind, just the phrasing here. So they're telling us that the wind is blowing from this angle of 125 degrees. So you'll see this, even if you pay attention to the weather, or you look online to see what the wind is, they often describe it as where the wind is coming from, rather than the direction that it's actually blowing towards. So here, the wind is blowing from a heading of 125 degrees. That's the direction it's coming from. So again, true headings, we start from north, and then we're going to rotate 125 degrees clockwise. So this is 90, and then we need another 35. So maybe like this. Now, this angle, this is 125 degrees, but that's not the direction my wind is heading. My wind is actually heading from that direction. So instead, my vector, I'm going to point it towards the origin. So then this is the initial point for the wind. 78 knots, so this has a magnitude of 78, so that's how long this one is. Okay, so now we have a vector to represent each of these. The answer we're looking for, the relative to the ground, we need the resultant vector. So let's put these two together, and we have a couple different options on how to find the resultant. One of those is using a triangle method. So we follow one of our vectors, and then wherever this one stops, we start the second vector, and then from the very first initial point, to your last terminal point. That creates a little triangle, and that gives you the resultant vector. Or you can follow the parallelogram method. That works as well. I'm going to use the triangle method just because I think it's a little bit cleaner. All right, so again, here's north, and then let's start with the plane vector. So then we'll just copy this. So starting at the origin, pointing about here. So this had a length of 310 knots. And this angle we know was 50 degrees. And then from where that vector stops, we'll start our wind vector. So starting from here, okay, then our wind vector, just trying to keep it somewhat parallel, like this. This has magnitude of 78 knots. Okay. Now, to get our answer, what we need is the resultant vector. And the resultant vector is going to be the one that goes from our first initial point here to this last terminal point. So this dotted line, this is the vector that represents our actual speed in our actual direction. Okay. The other nice part about using our triangle method is because we end up with this little triangle, we can use trig to our advantage. Specifically, the law of cosines is going to help us out a lot. So I have the two side lengths. To work with this, I do need a couple more of these angles. So let's think about this a little bit. There are more, there's more than one way that we can approach this, but just to give you one example, initially we drew our wind vector pointing towards the origin, like this. And we said that the angle all the way to that vector was 125 degrees. That was 125, right? Okay. Now what we did is we just took this vector and we translated it so that it was on the end of our plane vector. Okay, these two vectors are the same, which means that they're parallel to each other. So you can mark that. So these are parallel, and whenever we have parallel lines, we can find some alternate interior angles. So if I take the entire 125 and I subtract away the 50 going from the y-axis to my plane vector, that means that this angle is going to be 75 degrees. And then that angle is an alternate interior angle with this one inside of our triangle. This is also 75 degrees. Okay. Like I said, more than one way that you can think about that. I could also think about having, a little axis up here, just kind of drawing it in to think about it. So we can see where, that's 125. Okay, you can do the same thing with the parallel lines. But just to show you, what we're doing is we're translating this one to here, creating those parallel lines. All right, so now that we have that, I know a side length, I know the angle in the middle, I know another side length. We can use the law of cosines to help us figure out the rest of the information in this triangle. So what I want to find first is the length of our resultant vector. So I'm just going to call that x. That length is going to be the magnitude of the vector or our actual speed. So the law of cosines. So we have a side length. That one has to match up with the angle. So our angle is 75. The side length that matches up with that, the one across from it, is x. So then plugging everything in, a and b, 78 and 310. These are interchangeable. 2 times 78 times 310, and then our angle, cosine of 75. Okay. So let's do a little bit of simplifying. 78 squared, 6,084. 310 squared, 96,100. 2 times 78 times 310. 48,360 times the cosine of 75. Got some like terms you can combine here. 6,084 plus 96,100. 102,184. And then from here, remember we do just have to be a little bit careful with our order of operations. We would have to do this multiplication first before the subtraction. But instead what I like to do is I like to take the square root of that entire thing. Our calculator can help us out with that. So we have the square root, 102,184 minus 48,360 times the cosine of 75. And then what I get as a result, get 299.45 about. Alright, so that's the length of this side of the triangle. The length is the magnitude, and in this application, the magnitude is the speed. So this is 299 knots. Okay, that takes care of half of what you're looking for. The other thing we need is the actual direction of the plane. So really what I'm trying to find is I want to find the angle starting at the north and then rotated over to our resultant vector. And so maybe we'll call that angle theta. Okay. To find that, what I want to do is I know from my y-axis to the plane vector, I know that angle is 50. So if I can figure out how big this angle is on the inside of our triangle, I can subtract that one from 50, and that will give me theta. So let's call this one alpha, just so we can reference to it now. And now that I know all three sides and I know one of the angles, I can use the law of sines to find that angle. So we have the sine of an angle, and then we divide that by the side across from that, which is 78. And then we're going to do the sine of another angle. The only other one we know is the 75, divided by the side across from that, which is our 299.45. And then solving this, multiplying both sides by 78. And then we need to use the inverse sine. So then the inverse sine of this entire fraction and then typing that in. So we got the inverse sine of 78 times the sine of 75 divided by the magnitude of our resultant vector. And that is about 14.6 degrees. So this angle on the inside of the triangle is about 14.6. What I'm looking for though is I want to take 50 minus 14.6. And then that angle, 35.4, that is going to be our actual direction. So relative to the ground, because of that wind, the wind is pushing the plane a little bit. It's actually looks like it's slowing it down a little bit, so it's flying at about 299.45 knots. and it's changing the direction a little bit. It's changing its course. So instead of flying at 50 degrees, and let's represent this as a true bearing again, so we'll do 0, 35.4 degrees. There we go. So representing each of these with vectors, and then using some of our trig knowledge, we can find the actual speed, actual direction of our plane.